Hello everyone, and welcome to my short video presentation. The title of my project is Adaptive Multi-Partitioning for the Parallel Solution of Partial Differential Equations. But before we dive into details of the project, we need to clarify some theory which is very much needed to understand most of the concepts. Let's start with finite element method. In a nutshell, FEM is a numerical tool for solving a physical problem. The example below depicts how finite element method exactly works. First, we need to put the physical problem into well-defined mathematical formulation. When it's done, we can approximate solution by discretizing the geometry into finite elements and solving the problem on elements' vertices. Based on the discretized geometry, or simply the mesh, we can then establish linear system of equations. The goal of FEM or any other computational simulation tool is very simple: to be accurate and as fast as possible. Unfortunately, most of the times, it's a trade-off between these two attributes. The greater the number of elements and more precise calculation, the more expensive it is to solve in a system of equations. Can we do something about it? Of course. Instead of solving the system directly, we can use an iterative strategy. By assembling a matrix B and some initial gas xm, we can then compute next approximation xm plus 1, which will be closer to our desired solution. On every iteration step, we can also compute the residual R. Residual, or its norm, is usually a very good indicator on how far we are from the exact solution. The chosen iterative solver is called deflated conjugate gradient. Without getting more into details, DCG solver uses a coarse grid correction to speed up the convergence process. It solves a coarse system of equations directly and uses it to dump the low-frequency errors on the fine grid. Coarse grid is chosen by the arbitrary number of groups the mesh is splitted. The greater the number of groups, the finer coarse grid it becomes. For example, if we split the mesh into number of groups equals to the total number of elements, coarse system would become the same as normal system and it would converge in only one iteration, since we've already provided a direct solution to our system. Right now is a perfect time to state the aim of the project, which is a comparison of different methods for partitioning the mesh for the solver and analysis of their performance. Different types of method means different types of groups, which will result in different solver behavior. In total, 3 methods have been tested. The first method, purely based on geometry of the model, is called frontal approach. We first start with the first node of the first element and slowly assign each node to one group. When we are done with one element, we go through neighboring elements. Once we reach desired number of nodes per group, we simply close the first group and proceed with the algorithm, but now we are picking the nodes for our second group. This goes on until all of the nodes are assigned and groups are filled. The second method is called Spacefilling curve, in short SFC. It's also based on the geometry of the model, but in a slightly different way. To do SFC partition, we need to take a rectangular grid called the bin and then embed our geometry into the bin. Once it's there, we can fill the bin with its own elements and tie them to the original mesh elements. Our new rectangular mesh is ready, so we can start the splitting. The idea of SFC is to cause all of the 2- and 3-dimensional cases to 1D. This is why the method is called space-filling curve. We start at an arbitrary point and go through all the points one by one, creating a continuous line throughout the mesh. The rule of how elements are assigned to a group is just the same as in the previous method. Once we fill out one group, we carry on with the elements and start another. This part of the splitting is even simpler, since in 1D we only have one direction to go forward. The last method, called Matrixbased, may look as it doesn't belong to the same types of methods as the previous ones, but only at the beginning. Even though it doesn't explicitly use geometry to split the elements, it has a very strong connection to the mesh, quite like SFC method. How come? Each node has its own unique number, which represents one row in the linear system of equations, and each entry in the row represents connection between nodes. For example, if you take node number 1 with neighbors number 2, 4 and 5, It corresponds to the first row of the matrix with entries in the first, second, fourth, and fifth column of the row. Assigning the nodes to a group works exactly the same as in the frontal approach. We start at node 1, go through neighbors, then through neighbors of neighbors, and so on, until every single group has a right number of nodes. All of the methods were tested on a human respiratory tract case simulated by almost 18 million elements. Size of the problem and the complexity of the geometry was chosen on purpose to put the solver in the harsh environment. From all of the methods, frontal approach gives the best results. The total iteration number decreases fast in respect to number of groups, which is exactly the behavior we wanted to see. SFC is slightly slower, but still performs quite well in compared to matrix-based method. At the end, let's take a look how frontal method performs on various number of processes. Computational time plot in respect to the groups clearly indicates that the sweet spot for fast computation is from 1000 to 10,000 groups. Above that number, the influence of parallel communication becomes too big. This can be also observed on parallel efficiency plot. Lower group numbers holds on their efficiency, but bigger number drop basically immediately. That's all from me today. Thank you for your attention.